Thanks, Emmett. Well, what I'm going to describe here is a field study where I was looking for one thing and I ended up discovering things that I didn't even know were out there and I certainly wasn't looking for. And so this is the kind of way that science works sometimes, is that what we discover is not what we had set out to look for in the first place. Um, let's see here. Uh, well, how do I get it to advance the slides? Hmm. Let me go back to here and see if that does it. There we go. Um, this is the problem I ended up trying to solve, but it wasn't the problem that I started with. Um, you know that in current probabilistic fault displacement hazard analysis, it's 100% empirical. Uh, it really doesn't have a physical or kinematic basis. It's just based on observed data. Uh, but trying to make predictions based on bodies of pure empirical evidence uh, often ends up having a lot of uncertainty. And it's like trying to understand earthquake occurrence based solely on a historic record of earthquakes without knowing about plate tectonics or the seismic cycle of crustal faults. You have no physical basis to back up the empirical approach. Um, so as a result, in distributed faulting, we have large predictive uncertainties because we don't have an underlying physical model. And obviously, there's a lot of uncertainty in the PFDHA output. We want to decrease that. And the best way to decrease that is to come up with some physical kinematic models of distributed faulting until the model output converges with the patterns observed in historic ruptures. Okay, let's see if this is going to work. And true validation can't be just qualitative and subjective. It has to be quantitative. If we're going to try to compare model output to actual distributed rupture arrays that have been created, we need to somehow quantify what these distributed line patterns of ruptures look like. So I decided to treat distributed faults as a generic array of two-dimensional polylines. And they could be anything. They don't have to be faults. In DF, each polyline, which is a scarp trace, has some scarp-specific attributes. In the 2D XY space, the true line length is an attribute, the straight line length is an attribute, the sinuosity of each scarp is an attribute, and its bearing is an attribute. So, you know, the problem was I was looking at these patterns. These are all strike slip faults. Actually, these are some of the strike slip faults that were used by Peterson et al. When they created the strike slip version of PFDHA. And you can see that qualitatively, these patterns are very different. But how would we quantify these differences, which we need to do? Well, let's just talk about not only the attributes of each scarp, but the attributes of the array as a whole. The scarps have geometric and geographic relationships to each other. Um, One obvious thing is the distance of the distributed fault from the principal fault, and that's already built into PSHA. But other spacing issues, like the spacing between DEFs transverse to the strike, the spacing between DFs in the longitudinal direction, in other words, gaps in the DFs, the bearing of the long axis of the array, and the deviation of each scarp in the array from the overall bearing of the array. These are, I would call these array-specific attributes. Well, how did I end up working on this problem? I had started out working on a paper about Sackungen, created by the 2002 Denali earthquake. And the Denali fault, if you're not familiar with it, it's the San Andreas Fault of Alaska. It's a huge, long, high magnitude right lateral strike slip fault. And this slide here shows the Denali fault, which ruptured in 2002, and it created a beautiful set of ridgetop breaks or sackungs in here. And this was not the only place that had sackungs. There was another spot where the sackung field looked very different from this one. And I thought, okay, to quantify the differences, I mean, people can see them, but to quantify the differences, I'm just going to go to the literature and find how people have quantified arrays of linear features before, and then I'll just use that to compare this site to my other site. Well, what I discovered, there was no existing techniques for quantifying the geometric properties of two-dimensional arrays of lines. There's nothing out there. So I kind of had to reinvent the wheel, or invent the wheel, I guess. And so what I'm going to go through here in the middle of the talk is about this array and how I measured various parameters within the array of the sackungs. And then at the end of the talk, we're going to go back to how that applies to distributed faulting. This is a helicopter shot of the top of that ridge. You can see it's quite shattered. The Denali fault is off to the right, out of view here. And this is the system of ridgetop fractures. This whitish zone is the crest of the ridge. Here's the Denali fault down here. This is about 500 meters between the fault and the crest of this ridge that got shattered. And when I saw this, I thought, well, this is just a two-dimensional array of line segments. I should be able to characterize this geometrically with some parameters. But it's kind of interesting to see there's one wide part of the ridge. The ridge on this side is much steeper than the ridge flank on this side. This is mostly landslides here, which have truncated the sackungs that should be here. This is the only low gradient section of the ridge. Whoops, let me go back to that. And you can see it is symmetrical here where the ridge is wide. And it probably, there should be more visible sackungs over here, but the landslides have removed them. In cross section, all of these red ones on the southwest flank are here. This is the corresponding ones on the northeast flank. And in between them, there are some pure extensional fissures and grabens. Here's what they look like in the field. This is taken in this part of the field right here. And here's looking down the ridge. Here's where that cross section is in the broad part of the ridge. And we have a symmetrical array, I guess we could say here, of anti-slope scarps on both sides with grabens and tension fissures in the middle. And for some reason, probably due to the asymmetry of this ridge, This array is not centered on the ridge crest, but it's been shifted off of the ridge crest about 25 meters, something I had not seen before. And this is another Google Earth image here with the sun at the right. These scarps which face to the left are in shadow. You can see that reverses itself on the other side of the ridge because these scarps face to the right and these scarps face to the left. And in between are these features of pure extensional origin. Here's what they look like. And they have, since they were formed as a graben, clearly there's some kind of open bedrock voids below here because now they're full of all of these piping collapse features. Okay, so because I just wanted to get a quantitative metric to compare this Sackungen pattern with another one along strike on the fault, I just thought, well, what's the most simple structure of distributed faulting? It would be to have a bunch of distributed faults that were parallel to the principal fault, that were equally spaced, that were all as long as the principal fault. This would be the simplest possible geometric arrangement. That's not really what distributed faulting looks like, and certainly not what my Sackungen array looks like. It obviously, the distributed faults in that array have gaps in them along strike. So this is a little more representative or realistic representation of an array. A true array of distributed faulting, the faults don't have the same bearing as the overall array or the principal fault. And not only do they have a different bearing, but they're not straight lines, they are curved lines. So the true length of the scarp is different from the straight line length. So you have some sinuosity there. Here again, this is an image of all the 183 scarps in my array that I was trying to characterize. So here are a couple of the geometric parameters I decided to measure. The true length, which is LT here, is the actual length of the polyline. The straight length is just the straight line length between the two endpoints. The distance to the ridge, these black lines, this is like the distance of a distributed coseismic fault from the principal fault. The transverse spacing, that's the spacing between the distributed faults transverse to the strike of the array. And the longitudinal spacing is the gaps along strike. So these are pretty obvious things that can be measured and thrown into a spreadsheet. So after I measured these various parameters in the array for all 183 scarps in the array, I just put them in a spreadsheet here. And you can see what's listed here is the scarp cluster. There were 4 scarp clusters, A, B, C, and D. The number of the scarp within that cluster, the true length along the line, the straight length, the bearing, the deviation of the bearing from the bearing of the array, the distance to the ridge crest, the distance to the axis of the array, the distance to the next scarp along strike, the distance to the next scarp along strike, and then the sinuosity down here. So these here on the left are mostly scarp-specific attributes, and these things on the right are array-specific attributes. Okay, so here's the rest of the spreadsheet. And you can crank out mean parameters for any of these 6 or 7 parameters that I measured. And you can also convince Excel to get correlation coefficients between any of these parameters and the other corresponding parameters in the array. So what this shows here is the correlation coefficients between the true length of the scarp and the distance to the axis, the sinuosity, the deviation and bearing, the distance to the ridge, the spacing transverse to strike, and the spacing along strike. And what I was surprised to find is that most of these correlation coefficients were fairly low. These numbers here, 0.04, 0.09, 0.08, 0.01, that basically means there's no correlation. This is a classic way to graphically present correlation coefficients between multiple parameters. And you can see that each one of this is for cluster A. Here's the true length of the scarp, the sinuosity, the spacing between DFs in the transverse direction, the spacing in the longitudinal direction, the distance of the scarp from the ridge and its bearing. Each one of these bars is the correlation coefficient between those two variables. And you can see that here's the key to how strong the correlation coefficient is, and most of them are pretty weak. The one that I didn't even put on this diagram is the strongest of all the correlation coefficients, which is nearly at 100%. And it's the one between the sinuous length of the line and the straight line length of the line. Since those two numbers are almost always within about 5% of each other, the correlation coefficient's like 0.95. It wasn't worth cluttering up these diagrams with that. But these are the kind of diagrams that clueless geomorphologists with a lot of data try to use to understand cause and effect relationships. They look for the things that are most strongly correlated and then try to figure out, this correlation won't tell you which one of these is the cause and which one is the effect, which one's the independent variable and which one's the dependent variable. But down here on the left, I discuss or put into words what these three strongest correlation coefficients represent. This one, and this one. And they're right down here. I do the same thing for cluster B, but cluster B looks quite a bit different. In it, this link right here, it doesn't have a very strong correlation coefficient. And this was the second surprise to me, that I'm going to need a lot more data if these artificial subclusters, which I created in the swarm, are going to look very different. I need to look at the whole swarm as a whole. One thing that we can do pretty easily from this spreadsheet is look at the cumulative frequency of scarp lengths versus scarp length. And in this particular diagram right here, these are the percentage or the proportion of scarps longer than 1 meter, 10 meters, 100 meters, 1,000 meters. And you can see this cumulative curve becomes straight, which indicates this is a power law or fractal statistical group. And this is coincidentally also the kind of magnitude frequency distribution you get from joints or fractures in bedrock, as well as this is also the power law relationship that controls the spread of unconstrained infectious diseases, which we should all know something about now. Another thing that we can look at is in buffer zones, that step outward from the ridge crest. So that's like the buffer zones in PFDHA, which step out away from the principal fault. How much is the cumulative scarp length of distributed faults in those various buffer zones? In PFDHA, the equation says as you get towards the principal fault, the probability of having a distributed fault gets higher and higher. That's not the pattern that I'm seeing in these Sackungen clusters. The cumulative length of distributed faults in the Sackungen cluster does not continue to rise until it gets to the ridge crest, but it falls off. The maximum is actually found out here about 30 to 40 meters from the ridge crest. And as you get closer than that to the ridge crest, the number and length of distributed faulting falls off rapidly. And that is true here. That's true in this cluster. That's true in this cluster. It's not true in this cluster. For some reason, cluster C has the most cumulative length of distributed faults out 90 to 100 meters. How regularly are the scarps spaced transverse to strike? Well, this is the transverse spacing versus the frequency or the count. And the mean of all these numbers, and this is just, I think, cluster A data, so that's about 30 scarps in this data set. The mean is 17, but the mode is between 5 and 10. And it can be explained why the highest mode is here, then there's a secondary mode here, there's a tertiary mode here. When you're measuring the distance between parallel scarps, and one of those scarps has gaps in it, if you measure it in some places, for example, the scarp midpoint of the scarp you're trying to characterize, a right angle vector measured away from that scarp may hit the next parallel scarp, but if it falls in a gap in the next parallel scarp, it's going to pass through that gap and hit the second scarp, the next scarp beyond the closest scarp. So I think that is what is explaining this multimodal pattern here of frequencies. This diagram just shows a bunch of buffer zones. These are 10-meter buffer zones away from the ridge crest. And each one of these points is the midpoint of a scarp. What I realized after I began to investigate ways to characterize 2D data is that there weren't any existing methods for dealing with arrays of lines. But if I could turn those lines into a point and then use the length of the line as an attribute to the point, there's all sorts of statistical methods that will allow you to analyze the statistics of clouds of points. So that's what this is an attempt at. Each one of these points here, these red X's, is the midpoint of a scarp, which has a length. This one has a length of 21.7 meters. This one 32 meters, that one 8.5. So I just put the length of the scarp into an attribute table. Also in that attribute table are all the other parameters related to fault. It's bearing. So if you wanted to generate from this data set a map showing the lines that represent these ruptures, you could just tell it to draw a symmetrical line centered on each of these points with a 21.7 meter length and the bearing from the attribute table. That could be done. But what you can see here is that these numbers at the left are the cumulative scarp length of these distributed scarps in each buffer zone. They are the sum of the numbers in the buffer zone. So they range quite a bit. you can see within the first 10 meters of the ridge crest, there are no scarps whatsoever. Very different than the equations that we have now for principal faulting. And as we come down here, well, it looks like we were having kind of a trend here, and then the trend fell apart because in one buffer, there's only one little scarp. It's 5 meters long. As always in this kind of statistics, you can normalize this data and report it as the length, the cumulative length of distributed fault scarps divided by the cumulative length of the buffer itself, so that you'll be able to compare these numbers even if the buffer lengths and the various clusters are different. You can normalize the data, and once you normalize data, you can combine it, which is really how all PFDHA equations were generated. They were based on normalized data. Okay, so one other thing that obviously people who have worked with distributed tectonic faulting more than me is they say eventually with a lot of distributed faulting, it's hard to say which one is the principal fault and which ones are the distributed faults. And so thinking about this problem, I just generated a bunch of hypothetical arrays of distributed faulting, starting over here in the right, where there's only one. This is one length unit is the length of the principal fault here. And I'm generating little hypothetical clusters of distributed faults that are each one of which is 1/10 of the length of the principal fault. So in the simplest example over here, there's only one distributed fault, and the cumulative length of all the distributed faults is only 0.1. But as you get more and more distributed faults, by this point right here, the sum of the lengths of the distributed faults is now equal to the length of the principal fault. Certainly, with less distributed faulting, the principal fault is dominant. But by this time, you have as much distributed faulting as you have principal faulting. And then past that point, of course, the cumulative number and length of distributed faults is now getting longer than the principal fault. And it's at this point right here that sometimes you lose track of what's the principal fault and what's the distributed fault. Well, it turns out there are some approaches and even software made for analyzing two-dimensional arrays of lines. This is the fractured network analysis community. And in the examples that I've seen, which this program is based on here, all of their lines are straight lines or very slightly bent. Okay, they're not sinuous. And because they're straight lines, the input into this program is not the midpoint of the line, it's the two endpoints. Whoops, let's go back here. So they put in the endpoints, and then they use the old style. This is the way fracture densities and frequencies were computed before the software existed, when people would just manually run scan lines across the field and count the intersections. So this window scan line and circular methods are legacy methods from the analog days, but they've been now put into this computer program, and there's no reason that we couldn't use this program on an array of distributed tectonic faults or Sackungen faults or whatever you wanted to. This is just an example. This is a piece of the distributed faulting array from the Hector mine earthquake in California. And usually you want your scan lines perpendicular to the strike of the faults that you're trying to intersect. This gives you the best intersections. If you ran your scan lines the other way, they would miss a lot of these faults. You don't want to do that. I use the 25-meter scan line spacing here, and it works pretty well. It's just a little bit too large because there are some scarps that fall between the scan lines, so they're not detected. But the good news is, at this kind of scale, most of the individual distributed fault segments are nearly straight lines. So the fact that this FRONEP software makes them straight lines is not a problem. Let me hold on here. I got to give some power to the laptop. Okay. And the nice thing about FRONEP is it will output cumulative distribution curves for any of its parameters. And what this shows right here is some standard output from another model, not from my Sackungen cluster, but from another model, trying to fit to the data. These little dots are the data, trying to fit various predefined statistical functions and cumulative curves to the data. And clearly, in this data set, log normal is the best fit, even though most of the literature on fracture statistics say that they should obey or do obey power laws. And when I saw this log normal, the power law fit is pretty crappy here. Then I read this in the paper about FRONEP. It says that resolution effects or the presence of a characteristic scale imposed on a true power law distributed length data set can result in a log normal distribution. And so I think that's what happened here, because obviously there's some truncation in your data depending on how small of things and how large of things you can measure. Okay, so let's now go back to distributed faulting. Can we use any of these techniques to deal with the question? Well, in my mind, distributed faulting can represent one of two things. It's either the surface expression of a real bedrock fault, or it's the surface expression of rootless faults and fractures that affect only the unconsolidated deposits and were created by shock waves or differential or vibratory compaction. In other words, these things are not coming from faults in the bedrock. If a studied rupture, like a drone LiDAR survey or structure from motion mapping of all the zillions of distributed fault traces that we can see now, if that data set contains both of these types of features, no single kinematic model is going to be able to replicate them. So we would have to, if there's any of these in the data set, we have to identify them and remove them before any statistical tests. The present PFHA methods are all from, well, pre-2000 data mainly. They're low resolution data sets, and they didn't even contain all the fractures that we can see in the modern data sets done from LiDAR and drones. Now we can get a heck of a lot more data from these more modern technologies. In the legacy studies, the field parties that were walking around in the epicentral area after the earthquake just assumed that if they could see displacement on a fault and it was a long feature, that it was keyed to a bedrock fault. But actually that assumption has never really been tested on any rupture with geophysics, as far as I know. So now in the modern age, we can image thousands of these distributed fractures. Uh, what are we going to do with those new high resolution data sets if we combine them with the old low resolution data sets? We're going to be adding what we call apples and oranges. And so I think that's going to increase the uncertainty in the output of PFDHA. But at this point, if we get rid of all the low res data and only work with the high res data, there's so little of it that that too would also increase the uncertainties. So it looks like in the near term, the uncertainties in distributed faulting in PFDHA are almost certainly going to increase. There's only one way to dampen this increase, and that is to augment the empirical approach with other tools which help us say, the cumulative distribution should be following a distribution like this because of physics and kinematics. And that would help us maybe bring down the uncertainty. And fracture network analysis is one of the ways that we can do that, and we can do it relatively quickly. You just have to find somebody who can either manually enter the endpoints of the distributed fractures or write a script to do the same thing. So it can be input into FRANEP. We can test one hypothesis, whether every distributed fault in the array is underlain by a bedrock fault. If we go to a rupture where bedrock is thinly covered by quaternary deposits and then use geophysics to see whether every distributed fault is in fact underlain by a bedrock fault. I don't think this has ever been done. There's another hypothesis that DFs, and this is the hypothesis which is currently built into PFDHA, that distributed faults form randomly along strike at an empirical frequency specified by their distance from the principal fault. Well, I have a little problem with this because this implies that in the next rupture on this principal fault, the array of DFs will be completely different than it was on the previous event. It would be stochastic. But if the DFs are really tied to pre-existing bedrock faults in the subsurface, those faults can't move around stochastically. They are where they are, and where they're not, they're not. So I don't really understand how DFs can move around from event to event. I actually think the opposite, that the width of the DF zone and the patterns of DFs are fixed along strike due to subsurface buried blocks that are going to be there forever, so that the DF pattern in the next rupture is going to be very similar to the DF pattern in the last rupture. It's not a stochastic thing. It's more a deterministic thing. So anyway, that's the end of my journey. I started looking for one thing and I ended up